Thank you.
So you can see by the amount of authors that we try to put together a lot of information from many different taxa, and that's because the sandy shores, they lie in between land and sea. So that's a kind of issue, but it could be a fake issue because we tend to divide that's sea disciplines, that's marine biology, that's land things, and there are terrestrial ecologies taken care of. Furthermore, we have issues at political level. For instance, UNIS acknowledge just the stranded material as beach environment, which is not making our lives easier when we try to find out how to proceed. So this is a first attempt to merge different disciplines, and we have to be really rough with the approach, you will see. That's the amount of sandy shores you can expect. It's written in percentage by continent, and also the granularity of the information could be really fine, like at a few meters distance you can have two completely different environments. That depends on the wave strength, on the current strength, and on the winds. So they shape really in a fine way every single beach, and it gives them a kind of personality. So no beaches are alike. In fact, you see them close by in space. It doesn't mean at all they are really similar. In these, we have more complication. The most famous one is coastal erosion. The alarming news they come every day. It's faster than climate change, so I prefer to use the term coastal erosion. And also temperature rise, which is another broadly used proxy of change. And in this case, it's usually the 1 meter temperature, the 1 meter from the surface temperature that we use. So we decided to go again with common patterns and check what's happening. What engineers are saying, that their approach is that in case you have ongoing erosion, you can do basically two things. One is defend with infrastructures, and the other is let the land retreat. And they assume the whole system will move as is, like with all the components, all the interactions, all the functionalities backwards to the land. There is not much told about temperature changes because it's already a very warm environment, so it can reach 60 degrees under the sun in quick days. So there are studies made for humans. Humans apparently they will keep going to already warm beaches because they don't perceive any difference, but in cooler beaches they might feel the difference and the touristic pattern might change. But animals, they live the whole life there and nothing is done. So we wanted to check with beach resident fauna, and because that's the amphibole colloquium, I specifically target the talitrids. We gathered data. Some of them were from other studies, usually community level studies, and some were added. So the total amount is 38 beaches worldwide. We went across the whole range of energy exposure, so weight-dominated beaches, tide-dominated, sheltered by coral reefs, the whole range. Still, we know that talitrids are dominant in abundance in the temperate areas, so we try to be representative of that. Then we have one tropical area and one cold. In general, we sampled in the most convenient season. It doesn't mean that the warmest season is the most convenient. You can have this scenario, and then it's impossible to work on that. So it's usually spring we are talking about, when most biodiversity is out, and for the polar region is during the summertime, so when the light allows everything living there to come out. We had one common background, which was oops, the pitfall trapping. So we place a regular pitfall, 1 per meter, along the perpendicular to the shoreline. So indirectly we can detect by linear meter the amount of individuals you have, and we can derive the zonation. So we reanalyzed the community studies we had, and then we added the fringe environments. We have a decent amount of records, so that was allowing us to proceed with a global analysis, and we decided to go for trades. Now, I've been attending the workshop on traits of oceanic life, and there was a slide that it nearly made me cry. It was the overlapping of the marine knowledge and terrestrial knowledge, and then there was this overlapping part with a big question mark in between. So I had no theoretical background to move from, and that was quite scary, and that was the experts meeting. So I decided to be really rough with the approach, one trait being the breathing modality. On the beach, they need land and sea, so you have organisms that breathe air and organisms that breathe water. How to do this discrimination? We used worms by selecting marine extant species only. And the fact that traps are organized in transects means that we can detect, say, the distance from the sea line. So we had only the silhouettes because, of course, being harsh to find expertise, we didn't have much information about most of the taxa, but we did on talitrids. And you can see it's true that half of the organisms are air breathers, half are water breathers, but among the water breathers, the talitrids are the vast majority. That's good, because that's the right colloquium to present this. Then we use major repositories. The fact that they are open access was very nice because it means they start to be used. Usually these big data sets, they look for users, and we were one. We basically apply the coastal erosion. This is not complete yet, but it's a very nice visualization. The red is obviously erosion. The green is accretion, but it's still a change. And then we use the standard temperature rise estimation. We applied also some machine learning, which is a fancy way to remark what I was saying, that we didn't have enough ecological background to create very fine hypotheses, so we did just exploration. And we trained, as it's used to do for machine learning, on half of the data set, and we checked the zonation of the other traits divided a priori. So we divided terrestrial from marine, and the zonation was the response to it. We assessed the model two ways. One, to assess the goodness of fit, and the other was to assess the uncertainty of the model, so it's also another quite relevant information. And from that, we obtained a distribution, and from that we estimate the probability density in conditions of scenarios of 2050 and 2100. This is a preview that's only talitrid against the rest of the world, which is nice. I just wanted to show you. These are the species present in the data set, and they were identified by reliable people, so I'm really sure about that. We had the curious fact that there are no talitrids in the Arctic, but okay, it may sound curious because you saw all the gammarus yesterday. The gammarus was there; they didn't move from under the stones. So the environment is okay for them, but on the supralittoral there is nothing, and there is no water breathers in general. But there is fauna; it's just terrestrial. This is the two distributions. So the R square is from 0 to 1. You can see the marine organism is very good, and also the error, out-of-bag error, which is the uncertainty, is also quite low. For the terrestrial animals, it's a little bit different, but you can see the blue is the present line. Everything happens in all cases in the first part of the beach. So nothing happens on the dune side. This is still before the dune. One is just the base of the primary dune. And everything happens here, which means if there has to be an interaction among organisms here, the change is making the modality shift. So you can see the probability is going to be different in the next decades and in the next century. And we have these two peaks distance-based. So marine and terrestrial are going to converge from the sea to the same zonation. Why? I don't know. So I just make general considerations. One is that what I was saying, that the system is supposed to migrate, is not really correct. There are rearrangements inside and zonations, so something is going to change and is not an engineer point of view that we have to apply. And then it may be something related to the fact that direct developers, which are also water breathers, are more sensitive to temperature arrays. We need to study a little bit further on this point. And then, of course, what we change in terms of functionality. Talitrids are dominant, it's surely confirmed, and so we can go on studying them in a complicated environment. We just need a conceptual framework. In terms of traits, I think it's relevant because it really can span across disciplines. And to the next follow-up, we will see, hopefully, something.
Questions? Anya?
It's well managed. So I'm wondering about one of the last slides where you have this scenario, and the one that is different for more terrestrial and more marine taxa here, that it seems that for the marine one, in 2050, let's say, I understand that the animals are moving a little bit out from the shore, let's say water, but then with the next scenario, they're coming back. While for the terrestrial, it's just say the rise of the movement, but in the same place. Do you have any idea why?
Not really about this specific point. I see that there is a different response. That's something that I can remark, so we cannot consider everything at the same level. It was also remarkable to me that really it's just the first half of the beach, which is usually still humid, and it's allowing the permanence of both categories. The fact of the bimodality, I just interpret as a change. So we cannot expect the zonation and the whole life span to be in the same point. So something is going to change in space. Bimodality, this shark is strange also to me, but they are getting a more terrestrial profile without having the terrestrial adaptations. So that's a little bit scary to me.
More questions?
Thank you, Lucia. In your model, consider that species can move, but for the sandy beach at Node, where there is a strong erosion, there is no more sand, no more anything except concrete and soil. So the species can't move upward. The beach disappears completely.
If the beach disappears completely, I have unpublished data and it's on talitrids only. So we did the same forcing model, and apparently they start, the talitrids has a very sharp orientation on the seawards direction. They shift the direction parallel to the coastline. So it's maybe the last attempt to find a favorable habitat. In movement ecology, it means you assume the next habitat suitable is at reach within your lifespan. So you try to move somewhere. If there is just a little obstacle before a non-eroding beach, that's still fine. In case of defensive structures, you can find the next one. But you're going to lose the habitat, so you're going to lose all the species inside the eroding one.